So this is 12.5 in the textbook, titled Reaction Mechanisms. This section is really going to show us the actual truth behind a chemical reaction. I guess I've been lying to you for about 1.5 years now of how chemical reactions actually proceed. But that's just because their actual process is much more complicated than what we typically learn in a beginning chemistry course. Reaction mechanisms show us the actual guts of what a reaction looks like. There's a couple of things to remember. First of all, we want to understand that most chemical reactions actually occur by a series of elementary steps. So what we see in a particular chemical equation, I'm going to write one up here. Let's say we've got nitrogen dioxide, and to that we're going to add some fluorine gas. And if we combine these two individuals, we're going to actually get just a synthesis equation, and we'll get NO2F, and we're going to get 2 molecules of that. Now, up until this point, I may have said, well, what kind of reaction is this? And you said, well, it's a synthesis reaction. We're combining things, and it looks pretty cut and dry. When in actuality, there's small intermediate steps that take place in order to get to this particular point. The first thing that happens is we actually get NO2 to be added to F2, so it looks very similar to the black equation. But what's different is our product. We actually get NO2F plus fluorine. And the fluorine atom on the right side actually is all by itself. He doesn't attach to the resultant molecule for a small period of time. So there actually has to something has to happen to kind of coerce this fluorine atom to say, yeah, I'll go ahead and I'll bond and I'll make the final product. And that's where the second elementary reaction comes in, and it looks like this for this reaction. It's the fluorine plus NO2, and that actually yields again NO2F. Okay, so this is called a multi-step reaction. And if you kind of do some reaction canceling, some accounting of chemical reactions, you'll notice that the reds and the blue, or the red and the green reactions add up for the black. So the fluorines, they'll actually cancel each other out there and there. And the NO2s will combine. There they are. And the NO2Fs will combine. There they are right there, and that'll make way for those coefficients, right? So that's really how reactions occur. It's usually not one pretty, gorgeous little single step. It's usually a lot of very angry, ugly steps that make things very difficult to see. And so we are more likely to see some like multi-step reaction than these single-step reactions up here. The iodine clock demonstration that I did is a perfect example of this. That thing goes under like 8 different intermediate steps. So that red and green equation that I wrote, those are called intermediate reactions. And we call a species an intermediate if it's formed in one step and used up in a subsequent step. The fluorine atom was an example in the previous thing that I did, and thus is never seen as a product in the overall balanced reaction. So fluorine was an example of that. Intermediates are species that appear in a reaction mechanism but are not involved in the overall balanced equation. An intermediate is always formed in an early elementary step and consumed later. And again, I want to toss out another example of how this works. So you have 2 elementary steps. Although the combination of nitrogen monoxide and oxygen seems easy, it's a little bit more complicated. And the intermediate in this process, if we kind of take a look, is the dinitrogen dioxide, the N2O2. We can see that it is on the right side of the top reaction, on the left side of the bottom reaction. And so when we kind of add those two things up, go back here for a second, these things would be on opposite sides, so they cancel each other out. That's what leads to our overall reaction. Let's get a molecular representation of this kind of process. Here we've got nitrogen dioxide and carbon monoxide. That yields nitrogen monoxide and CO2. Again, this process doesn't happen in one single step. There's actually 2 different steps. Here we've got an NO2 molecule. Here we've got an NO2 molecule. Interesting enough, they break apart to form NO3, nitrogen trioxide, not nitrate. No, nitrogen trioxide. And then they also, on the other side, are going to produce NO, nitrogen monoxide. The second step of the process then is that's when the carbon monoxide actually comes in. So for this first step, carbon monoxide doesn't even happen, doesn't even take part. So when we get NO3 then to find the carbon monoxide, see it's this guy that will actually go say, hey, carbon monoxide, how are you doing? Let's react. And then they react together, and they produce the stuff out the back, which is this stuff, NO2 plus CO2. So we can see CO2 there and there. We've got the NO there and there, carbon monoxide there and there, and then the NO2, I think we've got that. Yep, we've got the NO2. I'm going to pick that one. That's going to be my winner because this guy goes away because of this guy. There we go. So interestingly, I'm going to clear all of this junk here for a second because it's a lot. Interestingly enough, one of the NO2s, one of the NO2 molecules, sorry about that, one of them appears and actually it cancels itself out in a later mechanism. So we actually call this guy a catalyst right here. This guy is a catalyst. So we'll get to that in a later video. All right. The intermediate, the two intermediates then I guess, you could say are one of the NO2 molecules and the NO3 molecule. Those are your intermediates. All right, we have three different types of elementary steps. We've got a unimolecular, unicycle. So it's a reaction involving one molecule. If the unimolecular step is the rate-determining step, I'll get to that in a second, we call that particular process first order. We have bimolecular. This is a reaction involving collision of two species. This would be a second order reaction. And a termolecular, which are really, really complicated and really crazy, and we cannot write integrated rate laws for. These are reactions involving the collision of three species, or third order. Now, I said something about a rate-determining step before. Okay, here we go. A reaction is only as fast as its slowest step. Kind of makes sense, right? It's like you're only as strong as the weakest link. Same idea. So you can have like 4 different reactions that go super, super fast, and they're all intermediate steps, and they go really, really fast. But if you got one reaction that takes like 14 hours to complete, guess how long your reaction's taken to complete? Yep, 14 hours. Okay, so you're only as fast as your slowest step. We call this step the rate-determining step. It determines the rate law and the molecularity of the overall reaction. So from that rate-determining step, we're going to be able to develop a rate law. Okay. A couple of things to keep in mind when you are determining the reaction determining what is the correct reaction mechanism. I'm going to call this, instead of bullet point, I'm going to call that 1. The first thing you need to keep in mind, the sum of the elementary steps must give the overall balanced equation for the reaction. If you can remember back to Hess's law, we did this. Second of all, the mechanism must agree with the experimentally determined rate law. That's the new stuff. We need to figure out how to do that. Okay? So we need to figure out this right here. All right. Well, let's look at this particular process. We have a 2-step process here. We want to know what the equation is for the overall reaction. Okay, so let's take a look and dissect our elementary steps here. We see a few things right off the bat. Hey, by the way, this is the diagram reaction that I gave you 2 slides ago. So again, we see that NO2 disappears. We see that, what else do we see? Oh yeah, NO3, bye-bye, see you later. Okay, those go away. And so we add up the overall reaction, and we get this guy, NO2 plus carbon monoxide, yields nitrogen monoxide plus carbon dioxide. All right, now, we want to know which one of these two, step 1 or step 2, is the rate determining step. What is the rate determining step? Well, first of all, let's attach this one. What's the intermediate? There you go, NO3. NO2 is also an intermediate, but it's a special intermediate. It's called a catalyst. I'll talk about that in a later video. What can you say about the relative rates of steps 1 and 2? Well, we can say that the rate equals K NO2 to the second. How do I know that? It was given to me in the problem, right here. That, as you notice, is the rate law for step number 1. Okay, NO2, right here, there's NO2. Where's that second come from? Well, there's 2 NO2s. So NO2 to the second. What does that mean? That means that step 1 must be much slower. It is the rate determining step than step 2. Okay? So there we go. All right, so a final example to see if we've got this nailed down. We've got this huge reaction between hydrogen bromide gas and oxygen gas to make water and bromine. It seems real simple, but my goodness, are there a lot of things going on. There's 4 different elementary steps. First of all, excuse me. First of all, we need to write the rate law for this reaction. Well, how do we do that? We refer to the slowest step, and we check out the reactants in that slowest step. Boom, we're going to write the rate law. There it is, HBr plus O2. Second of all, list any and all intermediates for this reaction. Okay, we get to see what things are created and then destroyed later on. Let's see. I got this guy, Huber, over there, whatever that is. Okay, that goes away with that one. I got 2 Hubers right there, and a Huber right there. So those all go away. Let's see, I've got 4 HBRs. 1, 2, 3, 4. I needed 4. 102, 102. That's good. How many waters? 2 waters, 2 waters. 2 bromines, 2 bromines. Hey, there we go. The only intermediates that I had was the Huber. All right. Well, 2 different Hubers. Huber and Huber. Okay, those are my 2 intermediates. We won't worry about this last point, the catalysts for the action. There are actually none in this particular process, but again, we'll worry about that in a future video. All right, that's reaction mechanisms.